In this video, I'm going to show you how you can train a UNet model to segment nuclei. So as we saw before, with UNet, we can estimate a label at each pixel, which is not going to be enough if we want to identify individual nuclei, but we can still try to find a trick. And here, the trick is to use an additional class, which is going to be nuclei contours. So if we can identify the inner nuclei and the nuclei contours, we should be able to separate them and then identify individual nuclei. So if I go back to the folder we downloaded from GitHub, if I go to local, UNet, in datasets, we have something which is called polynuclei. So we have a training and a validation datasets and a test directory where we have the images we want to segment. So if I go to training, I open the first image here. So we have nuclei stained with PAPI. And if I look at the corresponding masks, we have two different classes. The first one is in nuclei contour, second one is in NPI. And for all the pixels that are not part of nuclei contour or in a nuclei, they are part of the background. It's going to be the third class. I go back to the contours. If I zoom in, you can see that the contours that are between nuclei and background are 1 pixel width. The contours that are between nuclei are 2 pixel widths. This is intended to help model to better identify contours between nuclei. This, as before, I guess in validation, we have images that are smaller, 311 by 280, because we're going to train our model on images that are 256 by 256. Here, for tissues, we used larger images because we need more context. Here, when to write some nuclei, so we have large enough nuclei, large enough context to identify the nuclei. This wouldn't help to have larger images, actually. So let me go back to the notebook. I go to training. I'm going to open some same notebook we used for tissue segmentation. First panel to load everything we need, the codes and the packages, and then I'm going to do 4 training with 4 different values for loading rates. So first of all, training directory is going to be in polynuclei training, images and corresponding mask, validation directory in polynuclei validation, images and corresponding mask, and we're going to save the model in the same directory that we used for segmentation. So maybe we could have actually a directory for each kind of task. Here we'll still be able to differentiate them because we won't have the same number of channels. But it would be better to actually have a directory for each task. I'm going to keep this. So now we have one channel on NucleiDAPI, and we have 3 classes: background, inner nuclei, and nuclei contours for an imaging field of 256 by 256. I'm going to try with a learning rate of 1 for 100 epochs. No augmentation, and batch size we could increase it. I'm just going to keep it to 1 so it can run with GPUs that are not too powerful, but definitely we could increase it to go a little bit faster. And so now I'm going to use the same parameters: polynuclei training, polynuclei validation, models. It's correct. Just change the learning rate value 0.01, and then again training, polynuclei validation. Keep this value E-4, and finally polynuclei training, polynuclei validation, models, and E-. And I'm going to print these models. So 4 models, different values of learning rate. I'm going to speed up the video so you don't have to wait for a long time. go. So let's have a look at the accuracy and loss curves with TensorBoard. So it didn't work. When this happened, we can just change the port number and hopefully it's going to work. So first time you do it, sometimes it doesn't do anything here. It's fine. So here, I'm going to toggle everything because we also have the previous ones. And I'm going to go back. So if I want to see what is what, here you see we have UNet 2 channels, so that must be the segmentation of the tissue, the theory is strong. And then these are the first ones for nuclei segmentation. And here it's with a learning rate of 1. And when you look at it, obviously it doesn't work well. Validation in red is flat. When you have this, most of the time it means it doesn't change at all. It means that all the pixels got the same class. And here, probably the less frequent class because it's only 16% the pixels that are well classified. So just means that if you were to do it by randomly, and if you have the same proportion for each class, you would do a better job. So clearly it's failing. If we look at the results for a learning rate of 0.01, so here we don't see anything, it's just look at it like this. We see that it's much better, both for the loss is much lower, the accuracy is much higher. And the difference between the accuracy for addition and training doesn't look large. I'm going to remove the first two ones because it's not that. I'm going to remove this one and this one so we can have a better idea. It looks fine. So now let's see if we add the next one, which is for 1e minus 4, we see that training is very similar. If we compare validation, it seems a little bit better. In terms of accuracy, if I compare them, it's probably about the same. It looks like the one with e minus 2 is a little bit better, actually. And finally, if we look at e minus 6, here we have orange training and validation in blues. Validation is a bit better than training, which is a bit surprising. That can happen, actually. Just depends on the representativity of your validation. One thing is clear is that it leads to the accuracy that is not as good, that is lower. So it means that we are facing an underfitting here. So this is not as good. So we're gonna it with the loss as well. So clearly, e minus 2, e minus 4 will lead to very similar results. We could do some data augmentation. I'm not sure it would change much.